Hello everyone, Homer White back again with the second of our two-part series of screencasts on Chapter 9, Lists. So I want to show you a couple more applications of lists. One is returning multiple items when you are working with a function. So to set things up, there's an R function called incar that returns the number of characters in a string. So incar of Dorothy is 7. There are 7 letters in Dorothy. There's another function that works on strings, toUpper, and it makes all the letters of the string uppercase. So this call to toUpper Dorothy produces Dorothy. Now, say we write the following simple function, f1 here. It's a function of 2 strings called stir1 and stir2. And what we do is we compute the number of characters in string 1, the number of characters in string 2, and combine them together into a little numerical vector of length 2, and we call it numbers. And we make numbers into a named vector by saying names of numbers shall be the strings themselves. And then the final expression here in the body of the function is numbers. So when run, the function will return that named vector. And when we try it out here with Dorothy, Toto, then we get the name vector Dorothy, number of characters 7, and the next element is name Toto, and the number of characters is 4. Okay, here's another little simple function. Again, it's intended to take 2 strings, and so the parameter names are stir1 and stir2. And in the body of the function, the first thing we do is bind the name loudly to a little character vector of length 2 that's made out of string 1 converted to uppercase and string 2 converted to uppercase. And again, we make the strings themselves be the names for this vector loudly, and loudly is what's going to be returned. And we see the results of our function called f2 here. Now, we'd like to write another function that takes a string and returns the number of characters in it and the uppercase version of it. But there's a little problem in doing this. Suppose we try to do it this way. Suppose we said f3 is going to be a function of a string stir, and let's let number be the number of characters in stir, and let's let loudly be stir converted to uppercase, and then let's just return the concatenation of number and loudly. If we try it out where stir is set to Dorothy, we do get a vector of length 2, we get 2 results, but the first element is not the number of characters, it's the string 7, which is not quite what we wanted. Maybe we could try again. Let's define f3 as follows. Again, we compute number and loudly, but maybe we try to evaluate number and evaluate loudly. Well, when we call f3, where stir is set to Dorothy, the only thing that gets returned is the loudly. And of course, the reason is that a function returns the value of the final expression that it evaluates. The final expression this evaluates is the expression loudly. And so its value here, Dorothy, is what gets returned. The number expression got evaluated when the function was running, but it just got lost. It didn't go anywhere. It's not stored, it's not saved, it's not returned. We only got the string. If we tried it the other way, where we let number be the final expression that's evaluated, then it's the loudly that's going to get lost. So how can we fix this problem? Well, we just need to return one item. Why not let that item be a list? Because a list can have elements that are different types of things. So let's write f3 to be a function of stir, where again, number and loudly are computed as before, but the final expression that gets evaluated when this function is run is this call to the list function. So we're making a list where the first element is named number of cars, and it's equal to the number of characters in stir. And the second element of the list is named uppercase, and it's equal to the string in uppercase form. Now when we call f3 setting stir equal to Dorothy, we get this list in the output. And so now we can access the values as we wish. So if you needed to say use these, if you needed to use these values sometime later, then you could say bind the name results to f3 of Dorothy, and then results $ number of cars would be the 7, and results $ uppercase would be the Dorothy. So if you have to return multiple pieces of information, pack them together in a list as the final expression in your function. Next little topic is understanding ... You are going to see ... every so often in help files about R functions and in discussions about R code on the internet. ... is actually a special kind of argument that you can apply to a function. It stands for any other arguments that you want to add. Let me give you a demonstration here of a simple function that shows you how ... is working. So the function's name is going to be ellipsis demo, and it's a function of one parameter called ... And when the function starts running, it first cats out, did I get the following arguments? And then it prints out the result of making a list out of ... Now we're going to try ellipsis demo, where the arguments are x is 3, y is cat, and z is false. So notice, like x and y and z are not parameters in the definition of this function, not at all. But because the ... is there, they're allowed to come in, and R won't complain. And what happens is they become part of this ... that is fed in to ellipsis demo, and it can be made into a list, and then you see it printed out here. So what is this ellipsis argument good for? How does it help you in practical situations? You may remember the na.rm parameter from summary functions like mean. So like say you have this vector 2, 5, 4, 6, and na. And if you ask for the mean of vec, it's going to come out na, because the mean function is going to try to add up those numbers, and it can't finish the job because one of them is unknown. But you'll remember that there's an na.rem parameter to the mean function that by default is false, but if you set it to true, like in this function call down here, then the na in vec will get ignored. It'll just add up the 2, 5, 4, 6 and divide by 4 the number of actually known elements of vec, and we'll get out a result. Okay, so say you've decided that you want to write a function to compute the means of several different vectors that are inputs to the function. Look at mini-means here. So it's going to be a function of one parameter called vex. And by default, it's an empty list. But in reality, when you use it, it's going to be a list of several different vectors. We start by checking on the length of vex. And if it's an empty list, if the user didn't provide anything, then n will be 0, in which case we'll return the cat of, hey, I need some vectors to actually take the means of. But if it's a list of vectors that's of length bigger than 1, then we set up a little results vector. So that's going to be a placeholder numeric vector of length n. And then a loop, where in the loop, we store in the ith place of results the mean of the ith element of vex. Notice the double brackets that get us to the actual element, the actual ith element. When we're done, results is going to hold the means of each of those vectors that's in the vex list. And here we are just returning them. And so you can try it out. Mini-means on the list made out of these two vectors, the numbers from 1 to 5, the numbers from 6 to 10. The average of the 1, 2, 3, 4, 5 is 3. The average of 6, 7, 8, 9, and 10 is 8. Here we are trying mini-means on a list made of two vectors, 1, 2, 3, 4, 5, and 6, 7, 8, 9, and NA. So of course the second mean is NA. Now maybe you don't want that. Maybe you would like to always get a mean and not have any NAs. So you could just rewrite mini-means. This new version of mini-means is working the same way as the old one did, except when you're taking the mean of the ith vector, you remember to say na.rm is true. And so then mini-means of that same list is going to give you the 3 for the mean of 1, 2, 3, 4, 5, and 7.5 for the mean of the 6, 7, 8, and 9, the NA being ignored. So that's a nice attempt to solve your problem, but it does decide for the user that NA is going to be ignored. Is there a way where we could let the user decide whether na.rm should be true or not? Well, one elegant solution is to use that ellipsis argument. Look at this new version of mini-means. So it's going to be a function of vex with the default of the empty list just like before, but we provide ... as a second parameter. We check our input in the same way as before, and we set up a results vector the same way as before. And we have a for loop the same way as before, except that when we take the mean of the ith element in vex, we add on as a second argument the ... that the user passed in. So any extra arguments after the vex argument that the user puts in when he calls mini-means is going to get down here and become arguments to the mean function. So let's see how this works. If you try mini-means on just this one item, the list of the two vectors as before, then no second argument has been provided. And so then the ... here won't have anything in it. And so when R computes the mean of the vectors, it'll work with its default of na.rm is false. And so we get the NA as before. But look at this second function call to mini-means. The vex has been set to that same old list, but now comes in a new argument. na.rm is true. That new argument becomes the ... that's passed in to our function. And so now when the means are computed, there's an na.rm equals true where that ... is that's selected. And the result is that we get both means. So those are just two minor applications of the concept of lists. Lists are an incredibly useful and important feature of any computer programming language. Pretty much any language will have a data structure like a list, where you can just pack into it objects of all sorts of different types. We've only just scratched the surface of what you can do with lists in R. If you continue on to Computer Science 2 or to our data science sequence, you'll see lists all the time. Well, that's it for Chapter 9 and for the standard portion of Computer Science 115. See you later.